各位都知道，上半年我们出现了一个很严重的攻击事件，叫做 Wanna Cry， 然后就想哭。那大家其实也都知道，这个 Wanna Cry 是透过 MS 07011这个 SMB 的 exploit，Windows exploit。那这个 Windows exploit， 它是从美国 NSA 流出来的军火，就是从去年开始有一个事件，就是美国其实就是有一些相关单位，它已经开始研发数位军火，这是第一起数位军火外泄造成民间受害的案例。那么，其实我有问过尼克老师，他其实对于这些细节，什么 NSA， 他其实是不能讲的。但是呢，对于细节的部分，像是你怎么确认这个漏洞的技术细节，他都有在这一个演讲里面会提到。那各位如果有兴趣的话，这一场演讲是非常值得听的。好，那我们掌声鼓励尼克老师。
Hello, hello. Well, thank you. I have no idea of what you said, but that's probably good. Well, thank you, guys. I'm quite delighted, actually, to be honest, to be standing here before you. So yeah, I've heard "Wanna Cry," I think. So yeah, I did actually understand that. So he's right. I'm going to talk about SMB today. But yeah, guys, don't be mistaken. I'm not dropping any 0 days here. I don't want to be fired. All right, let's start that. Yep, that works. I can't believe that I'm doing this presentation on a MacBook. That shouldn't happen. So let me take some time to introduce myself. So who am I? Well, I'm Nicolas Joly. I used to be an exploiter, so I now work at Microsoft, but before that, I used to work for a company that you might know, guys. It's called ViewPen. It was called ViewPen. So we were doing exploits. We were doing some vulnerability research, doing some 0 days. And I do remember one day that was in Consequest, so before I joined Microsoft, and I was sitting at a table, and there was one guy from Microsoft right in front of me, and he told me, "Nico, we've never met, you don't know me, but I know your work really, really well." I was like, all right, I don't know, I'm not very sure about what you're talking about, but So yeah, I'm now working for Microsoft, so the MSRC, so Microsoft Security Response Team. So what are we doing there? Well, we solve crises. Well, it's not only about solving crises, but crisis happens from time to time, and typically with the kind of stuff that I'm going to talk about. No? But yeah, we are more like focusing, or actually in my team, on anything that has to do with exploits, vulnerabilities, writing mitigations, just to make it hard for you guys, so that your next exploit will take probably forever. We'll see. I'm quite confident about that. So I'd like to start this story again from Twitter, as always. So I do remember that day. There was a Friday in April. I was again traveling in Asia, in South Korea. And so for that conference, whose name is HITCON, so it's about 0 days, of course. And so that was a Friday night, so we were going to a restaurant, and I quickly checked Twitter. And, you know, on my feed, there were like stuff about these guys, so shadow brokers. So just a quick question, guys. How many of you have heard about WannaCry or the shadow brokers? Anybody? All right, not many people. So yeah, checking my Twitter feeds, so apparently there was a release of like several exploits just dropped to the public. So I didn't have anything with me, so quite hard to just assess if it's true, if it's false. And I was like, Okay, so that's probably synonym of a crisis coming up from the MSRC. And then another tweet like 30 minutes later saying, yeah, it's about 0 days and probably affecting the SMB protocol. And I was like, oh no, not again. And then a few hours after, one guy, a British guy, on Twitter again, saying, oh God, it's going to be a bloodbath. There's exploits, they do repo on the latest versions of Windows. And when I saw that tweet, I found that is not possible. What did we miss? What did I miss? That shouldn't be, that shouldn't happen like this. And so I went to sleep. And then on Saturday morning, I checked my Twitter feeds again, and there was that blog post from Philip Miner from the MSRC saying that the team during the night, my night in South Korea, had taken time to review all of these exploits, and it turned out that most of them had been fixed. So this is, I'm going today to talk about the SMB exploits. Some of these exploits affected, for example, Exchange. Yeah, I won't be talking about that, only SMB. So these exploits were indeed fixed. So what are we talking about here? We're talking about a fix that was released in March. So as you can see on that slide, so there were 6 vulnerabilities. 5 of them were critical. The last one was an info disclosure vulnerability. So yeah, I mean, I've heard about these bugs at some point in 2017. Actually, I was on vacation, because it's always about that when this kind of thing happens, and was skiing in France in the Alps, and quickly checked my emails, and apparently there was some stuff going on about SMB. And you know, guys, I used to be well, an exploiter at ViewPen, like mainly working on Flash or JavaScript or this kind of thing. And SMB, I had no experience with that. But I read that thread, and well, it sounds quite interesting. So let's talk about that more into details. So for this presentation, I'm going to talk about the vulnerabilities that were used by these eternal exploits. I talk about also how these exploits work. I will mention our mitigations for Windows 10. And then in the end, I will be talking about some of the research we did alongside, like some other bugs we fixed. So let's start with probably the most famous one, the Eternal Blue. So why do I say that this is the most famous one? Because for some reasons, this was the exploit that was adapted and ported to WannaCry. Don't ask me why they choose this one in particular. I have no idea. I don't know. Well, I don't know. So this exploit was abusing a vulnerability, an integer wrap. So what is that thing? So just on these slides, I've put the relevant snippets that you guys can have a good idea of what this is really about. So yeah, so integer wraps. So what is that thing? So usually when we've got this kind of vulnerability, if you talk to me about an integer wrap, I will be thinking about some bugs in an image parser. Like typically, you're dealing with a JPEG or a GIF image, so the sizes, the dimensions of that picture are held on 2 bytes, and an attacker has put I don't know, a width, for example, he has set it to 0xFFFF. And then, for some reason, the parser, well, the renderer is going to allocate that 0xFFFF plus 1, which is going to wrap on 16 bits. And then there will be an allocation, and then an allocation of 0, probably. And then data will be returned to that buffer, causing, of course, a heap overflow, and then triggering remote code execution, etc., etc. In that case, this is a bit different. So as you can see on this picture, there is that function, well, that's not a function, that's a macro, which is pointer diff short. So what is this about? So let me first introduce you to 2 structures. this one, so this FEA list, which is supposed to embed several EA items. On the structure on your left, you can see that these FEA items are, well, there is something missing here, but basically these FEA items, they contain, there's 3 members plus 2 other buffers. So their size can actually vary. So what this bug is all about? This is about processing a list of items. This is about pre-processing, a list of items in order to determine a size, to allocate data, and then write to that buffer. So how does that work? The source code is quite big, so I didn't want to put it there. So I just pasted a screenshot from IDA. It shows that there's a loop, and that loop is actually iterating for all these elements in that list, and it's assessing their size. So usually when we talk about the SMB v1, so that all protocol, we are talking about messages that shouldn't be more than 10,000 bytes in X. So very small messages. So in most circumstances, this function will just behave fine. But as we are talking about exploits and vulnerability, we are, of course, talking about edge cases. So what happens there? So let's assume that somebody sends a massive packet, so a packet containing more than 10,000 bytes. So that function that I just showed you at the slides before is going to loop to process all these items and determine a size. It's going to determine the last items that is valid in that packet. So basically, you're sending a packet to a server, and you're telling the server that there is, I don't know, like 20,000 bytes in that packet. So server is going to just check if you're telling the truth, and it will accurately calculate the amount of data needed. And of course, here is where the bug stands, because if you've got enough data, you're going to wrap that counter. And so because of that integer wrap, the server is going to believe that there is actually more data than there is. So it's going to allocate a buffer according to a size, but then there will be a loop that is bounded by the last valid element. And because of that bug, that last valid element is going to be outside of scope. And so we'll hit direct buffer overflow conditions. So so that's pretty straightforward. You just allocate data, and then you write past the bounds, and that's it. So a stupid bug. How did these guys exploit it? I believe, I've seen exploits in my life so far, and I do believe that the guys who did that are quite smart. If I had to exploit that thing, I would think about abusing an object directly into srv.sys, that SMB1 library. These guys, they did it a bit differently. Instead, they used some object populated by srvnet, and these objects are created actually when you create a connection to port 445. So when you send a SYN packet to port 445, the server is going to allocate a new MDL, so a memory descriptor list object in the pool, and it's going to initialize some structure there. And that's where the fun begins. Because these guys, what they did was to sculpt the heap so that their buffer, they were going to sculpt the pool. Let me use pool instead of heap here. so that buffer that they were going to overflow would be placed right before these MDLs. And then, after triggering that overflow, they would overwrite one MDL with some control data. And this is where it gets interesting. Because how do you exploit that? Well, it turns out that these MDLs contains a pointer that can be used to write the data received by the connection. On this picture that you can see on screen, the second part is just about sending data to these connections. So what happens? So we are allocating an MDL, and then we are overflowing on it. And then we are just using some pointers in that MDL to write data to, somewhere in memory. But since now that data has been overwritten, we are now able to write some data arbitrary, to an arbitrary location in memory. And this, of course, runs with kernel, in the kernel, so with the highest privileges. So it's pretty much game over. So what did these guys do? Well, actually, it was quite straightforward for them. So this exploit only worked up to Windows 7. And on Windows 7, the HAL region can be executable. So it can be executed. So what they did was just they abused that arbitrary right to send their payload to read, write, execute memory page, and just have another function pointer overwritten in that structure, in that MDL structure, to hijack the execution flow. Yeah, that works. On Windows 7, at least it works. It doesn't work on other systems, but on Windows 7, yeah, I have to say that this works. And so is it why this exploit was adapted to WannaCry? Yeah, perhaps, because it's quite simple. So there was one guy who tried to, and actually who managed to exploit it for Windows 8. I'm not sure exactly why he did that, but on Windows 8, the system behaves a bit differently. So this HAL region is not executable. So the guy had to trigger that bug twice. So first to set the NX bit to 0, and then trigger again the bug, while just to have the same behavior. I haven't seen any. I don't think I've seen any successful port of this particular vulnerability on the latest Windows 10 versions, but I believe it could be potentially doable, but that would be quite a challenge. How this thing was fixed? Well, as I show you in my first slides, all this had to do with that pointer diff short thing. So it's quite weird to see that macro. I mean, pointers, even on a 32-bit system, they should be on 42 bits. So yeah. So the fix for that was quite straightforward. We just changed that pointer diff short to pointer diff, and instead of writing a short, then we write a long, and that works. Is there any other places where this vulnerability could have been found? So there was another function very similar to that function that I can't pronounce the name. Yeah, it was fixed as well. Is there any other function that use this? Not that I'm aware of. So we should be safe. Let me talk now about Eternal Champion. So this one was about abusing some race conditions. So this one is quite good. Race conditions. So what this is about? This one is about abusing transactions. So let me first talk about some transactions. So in SMB1, you've got three types of transaction. Anti-transaction, transactions, and transactions too. So how does this thing work? So basically, you've got your client and you're talking to a server. So you send a transaction request, and the server is going to reply with a transaction response. Yeah, that's quite simple. That transaction request, it has several fields. So on these fields, you, for example, specify the amount of data that you're embedding. You specify the number of parameters that this packet contains. You specify the number of setup bytes also. So this is all for some internal use for SMB. And it is also said in the specification that if your transaction packet is too large, then you can use some secondary transaction packets. And in that case, it's quite simple as well. You send a primary transaction request. Server says, OK, send me more. And then you send the other one. So how do you specify that you need more packets? Well, there is a field in the transaction object, which is called max. There are two fields, actually. These are called max parameter count and max data count. And so basically, if data count is different from max data count, or if parameter count is different from max parameter count, then the server will know that more requests need to be sent by a client to process the transaction. That's quite simple. That's how it works. And then goes the funny thing. What happens if right after the first transaction, then we send an unexpected secondary transaction? Let's say that we have one transaction with data count equal, I said some nonsense. It's not max parameter count or max data count. It's total data count and total parameter count. I come back to the others later. But yeah, so basically you've got a primary transaction and you've got data count equal total data count. And now the client said a second transaction, so secondary transaction. This one is unexpected with another data count. So it turns out that the code in the secondary transaction is quite robust, I'd say. At least you cannot have like a stupid buffer overflow. I mean, for example, specifying a data count which is greater than total data count. Yeah, the server is going to reject that. But what the server does not is validating whether or not that primary packet should be completed. So, which means that if you send a secondary transaction and that the first packet has already data count set to total data count, yeah, the server just won't care, and it's just going to increment that data count. And here is the bug. So you end up with the primary transaction being executed while data are still being appended to that first transaction. How did these guys exploit that? This is, if you take a Wireshark capture of these exploits, you'll quickly see that it starts with a funky packet. So this TCP packet, it embeds 8 SMB, I think. The first one is a primary transaction for the NT-rename function. So I talk more about this function later, but this function basically does nothing. It's like the SMB echo function. You send data to it, and it will reply with the same data. So this is the first SMB. The second SMB is a secondary transaction, one that is not expected. And all the other SMBs are just to create some transactions in the pool. So what happened? The thing is that these guys, they were quite clever, quite smart in the way they did that. Because their first transaction, it is set to contain more data that the server can just handle in one request. I'm saying here that the server will need to send at least 2 responses to complete that transaction. This is because the buffer is too large. So the server, when it gets that first anti-rename request, it is just echoing the first transaction, and then it sees that this request has more data than what the response can contain. So it's just going to queue up another request, another response in another thread. And this is where the race condition happens. Because on the second SMB, there is a secondary transaction that is going to increment that data count. So when we enter the code that is responsible for parsing that secondary transaction, we are going to increment a field called inData. And also, we are going to increment that field called data count, and then we write data to the inData buffer. But this, we don't care. The only thing that matters here is the fact that we are incremented in data, because this data count, because this data count will be used in the end in SMB, a complete execute transaction to fill the second response. And this is where these guys managed to leak memory, because so initially you have your inData buffer, which is pointing to a valid location in the transaction object, and then you increment the data count. So now the server has just no idea that it's going to leak memory, and this is exactly what happened. So these guys, they exploited that issue first to leak memory. And yeah, on that picture, you can see what they leak. Basically, some pool headers, so to know to know the architecture of the server, and also some pointers, for the next step. So what is the next step? Yeah, this bug is not only about leaking information, it's on RC. So it's where it gets a bit more interesting. There are some functions. Well, in SMBv1, there are like tons of functions that you can reach with just one transaction. So there is one, which is that query path information function, which is using that inData field. And actually, it's resetting it to a stack buffer. And that's quite bad, because in this case, when we are eating the secondary transaction, we are going to use that inData buffer again to write data. We didn't care about that when we were leaking memory, but here we do care about that, because when we are going to use that inData buffer, we are just going to write data to the stack, and this does not make any sense. This should be pointing to a pool. So we end up with a nice stack corruption, which can be abused, of course, to execute arbitrary code. So the fastest way is, of course, to overwrite a return address on the stack and have it pointing like somewhere in the pool. On Windows 7, it doesn't make any difference. The pool is executable, so you can just return anywhere and have your shellcode executed. And that's it. Again, that's quite a simple exploit, quite a reliable one, and and quite a disastrous bug as well. So how did we fix that thing? The fix for this one is a bit complicated, because these transactions, they are just all over the places. So what we ended up was to to use that execute flag for a transaction. And so whenever a transaction would be executed, we would set that execute flag so that in case a secondary transaction would come, we would see that this execute flag is already set, so we should just drop it. That was a part of the fix. Another part was to add lock pretty much everywhere in the code, so that to be sure that no other race condition can happen. So typically you've got a lock on the connection object, and each time that lock is set, then you can be sure that there won't be any other thread writing data or using this transaction. I hope that this fix will be robust. We'll see. Let's talk now about another one, Eternal Romance. This one was abusing two separate vulnerabilities. I quite like this exploit. So the first one was again an information leak. So we are again talking about transactions here. That's at the very heart of all these exploits. So this memory leak happens when you send a transaction and you try to read some bytes from a pipe. So there is in a code for SRV pick name pipe, restart pick name pipe, there is something at the end that specifies how much data is available in the pipe. And what went wrong here is that we failed at checking whether that amount of data was actually fitting in the transaction object. So in the transaction object, you've got a pointer which is called out data, and the response, so the packet returned by the server would take that pointer and would copy data count bytes from this pointer and send them to the client. So since we are not validating that data count, this is where the max data count that I was talking about earlier comes into action. So the client is actually specifying the amount of bytes that it can handle. And so in this exploit, for example, it was set to 1. So which means that only 1 byte could be read, should be sent by the server. This of course didn't work. And what happens is that instead, well, the server would just leak memory starting at some crazy offset in the transaction object. So I was talking about a crazy offset. Why is that? So these guys, what they did is that they specify the max parameter count to be set to 0x 5,400. And why that number? Well, it turns out that when we allocate a transaction object, there is some code that checks how much data we want to allocate. And these transactions objects, they are like the perfect target for an attacker, because these objects, they can be as big as you want. And these guys, so they specify that max parameter count to that value, so that the in-data buffer would point at the very end of the packet. And since the size of the minimum size of a transaction is almost about this value, so that would lead the server to read data after the bounds of the transaction object. So here we've got our memory leak again, and we are able to leak data, the architecture, etc., etc. Let me talk now about the second bug, and that's quite my favorite one. This one is disastrous. So before that, let me talk about des requests, des write annex request. So with this request, you're normally supposed to write data to a file, to a pipe, or something like this. And according to a specification, if you've got a lot of data, you can split this request into several. And so how does that thing work? It's pretty much the same with transaction. You've got this field, total data count, and you've sent data count. You see that data count is lower than total data count, so you know that more packets are coming. And how the server can find that packets? Let's say that you send like 5 different write annex requests, all of them requiring more data. So what happens is that the server is going to use a function which is called SRV find transaction, based on several information found in the packet. And this is where things go wild. There's this find SRV find transaction, it's also used in the transaction request. So in the case of the write annex request, when we write data to the transaction object, we are using the in data pointer. But in these particular cases, each time we receive some data, we are incrementing the in data pointer. And this is where things go bad. Because if you look at the code for that handles the secondary transaction, you'll see that instead the in data pointer is always remains the same, which means that we can have a transaction crossover. This is how we called it, where you have a write annex request followed by a secondary transaction that will be abusing that in data pointer. And this is disastrous, because now you're able to write data out of bounds of the transaction object. And the crazy thing about this is, of course, the offset can be controlled. So you've allocated your object in the pool, and you're able to write data basically anywhere after that. So it's a really interesting bug in terms of writing an exploit. So how did these guys exploit it? Well, if you try to exploit that bug, you'll soon figure out that it's really, really easy to have an arbitrary write primitive. This is because transactions object have been made such that there is a pointer to the in data object written at particular offset there. So if you spray the pool with several transaction objects and you happen to override that pointer, then you'll be typically able to write data at an arbitrary location when you send a secondary request to the transaction object that has been overwritten. Regarding more of their exploit, there is something that I'm not very sure of. That these guys, they used a sequence of 3 different transactions to exploit that issue. 2 are enough. Trust me about this. So these guys, the difficulty actually here is to get an arbitrary read primitive. And what these guys did, they first overwrote the in data buffer of a second transaction in the pool, and then they used that second transaction to override the out data buffer pointer of a third transaction in the pool. Well, that works. In the end, you would just be able to reference that third transaction to read data anywhere in the pool. And yeah, that indeed works, but it just required an additional transaction. I'm not sure exactly why they did that, but in the end, it works. So once they had that read and write primitive, what did they do? Again, we are talking about Windows 7 here. We'll talk about another exploit later, but this thing was just about like finding a read, write, and executable section somewhere in memory. So yeah, so on Windows 7 you don't have anything like this. So what these guys did was just to reference somewhere in the pool that would be, of course, executable, put their data here, and that's it, and job done. The only thing that is, let's say, remarkable is that to trigger their payload, they, instead of just like, I don't know, for example, overwriting a stack pointer or something, they instead overwrote a pointer in an array of a function in a dispatch table, so that with a particular SMB request sent to a server, they would be sure that they would get code execution. So that was quite a good exploit. Yep. So yeah, I just talk about all of this. Hold on. Oh yeah, I was. Yeah, sorry guys. So let's talk now about eternal synergy as the last one. So this one actually doesn't use any other vulnerabilities. So what you can quickly see when you do a Wireshark capture is that the first packets are sent just to trigger the memory that we saw in Eternal Champions. So again, they use that race condition, which is quite reliable to leak memory, and that's it. The next step was to get the RC, remote code execution, and for that they use the exact same bug as Eternal Romance. The only difference between Eternal Romance and this one, Eternal Synergy, is the target. On this one, these guys, they wanted to target Windows 8. And on Windows 8, the pool wasn't made exploitable. So they had to figure out a different way to execute their code. But it turned out that on Windows 8, the NT binary, you can see that there are some read, write, and execute sections in it. So what they did was just abuse that read and write primitive that they had just to write their data to that section. And then, yeah, the remaining was exactly the same. They overwrote a pointer in the dispatch table. And then, yeah, that was it. You just send a particular request to that server, and you got your code execution. So, yeah, quite a good exploit as well. None of these exploits worked directly on Windows 10. And yeah, I mean, I'm an exploiter, so I thought I would have preferred to see something like this. I mean, a cool exploit for Windows 10 is not something that you see every day. But on Windows 10, and specifically on the latest versions, we've got several mitigations that make this exploit fail by default. So, for example, all these features like executing data in the pool, yeah, this is gone. This doesn't work anymore. So I know that you guys are hackers, and I believe that if you know about something like this, like how to make the pool executable or how to find like some read, write, and execute section somewhere in the kernel, you should probably report it to us, because I believe that it might qualify for the bounty submissions, and you get, of course, a reward for that. The other thing that I quite like is now that we've got kernel CFG. So you cannot just overwrite like a pointer in a dispatch table and just have it executing. Yeah, that won't work. The system won't let you do that. You can always try to bypass it, but yeah, you probably spend some time on it. And then, yeah, the last mitigation that I'm going to talk about is the fact that on Creators 4, so which will be released later this year, SMB v1 will be disabled by default. So yeah, we don't want anymore this protocol. This doesn't mean that we are not going to support it. We do care about this. If you've got some bugs, we will fix them. But we are just going to deprecate it. These things date back from so long ago. Yeah, it's time to move to something more secure. So what else did we do? So I just focused so far on 6 bugs that we've received. When I saw the 6 bugs, I was like, oh, there must be others. It's not possible. These bugs, they were so critical. Yeah, there must be others in the code. So we did some research on that code, so I was absolutely not familiar with that. And in the end, I believe that we fixed 20, something like that. So on the next slides, I'm just going to show you a few of the bugs that we fixed. So I start with a pool overflow in that create options function. So when you look at the code, so that code is quite huge, actually. So I believe that the srv.sys DLL is around 300 kilobytes. So there are still like a few functions to look at. And so we essentially focused our research on the transaction area. And for example, when you look at this function, which can be called, for example, with an SMB open request, you can see that there are some checks at some point whether the SMB contains some extra arguments. It turns out that in this case, for example, we were not checking correctly if the size of the allocated out data buffer was enough. So we would end up with an out-of-bound write of 20 bytes in X to a pool. Yeah, we don't want that fixed. What else? Something a bit more subtle, let's say. In the anti-transaction code, this code is very complicated. It's quite ugly to look at, if you want my opinion. But anyway, we had a look, and you can see that at some point, the code is making some assumptions on different values set in the transaction. And one of them is the setup count field. We haven't talked about that. So at one point, the code was making an assumption on setup count, and at another point, it was making another assumption, but this time based on max setup count. So since the two values are different, they are not the same, so we had like, yeah, there was an issue in that code. So this would typically end up in another pool overflow in the code, and of course we fixed it. What else? Something I'd say a bit more subtle, but yeah, when you look at the code for restart write name pipe, there is this function is quite small, but there is something. It's resetting some values, and then you see that it's trying to write something to the out parameter buffer. But the thing is that we've got these fields like max data count, max parameter count. These fields are specifically used to allocate the out parameter and out data buffer. But in that case, there was nothing in that code that was checking if we could actually write data to that out parameter buffer. So in the worst case, we would go off by 2 here. This is fixed. Let's come back to that anti-rename function that the shadow brokers have been, the shadow brokers, I mean, whoever wrote these eternal exploits have been using. So what is that function? That function actually does nothing. As I told you before, it was just similar to the SMB echo function. It was just echoing the original packet that we sent. So what we thought was, for an exploit, this function is amazing. It's amazing. Say that you've got a big transaction and you're calling that anti-rename function, and then you use, for example, the out-of-bound issue that Eternal Romance was using to overwrite some fields in the transaction object. And since that the original buffer is huge, the server will need 2 response, at least, well, the server will need to send 2 packets to a client. And because of that function, there was absolutely no validation on the data count, parameter count, and setup count values. So you could just overwrite these fields and read back like anything you wanted in memory. And this was even worse if you were thinking about this bug in the secondary function transactions, where you would be allocating data, and then you could specify an offset where you wanted to write data to a buffer. So here we had like an uninitialized memory issue where you could actually choose the offset where you wanted to write data and then dispatch later that object to the transaction function. But nothing was actually initializing the buffer allocated. So what you could do was, for example, target the anti-rename function with some large transactions and just constantly set the offset in the secondary transaction to 0 so that the entire buffer would be left uninitialized. So this is what we call a heap visualizer and a remote one. We don't need that feature, fixed. What else? Something that I sometimes ask in interview. So in C, you can define some structures, and in the structures you can have different variables, different types. And in this function, for example, a snapshot function, you were using a snapshot structure, and this structure had defined a buffer in the end, a buffer of size 1. And it turns out that in some specific case, when snapshot count was set to 0, we would just return that buffer, that structure, but without having it fully initialized. So we could be leaking here 2 bytes to the client. That is fixed again. Something a bit more interesting in the IOCTL, in a function that handles some IOCTL. There was that code that was used actually to return some data to the client. But that code was actually using a fixed value. And in some condition, it was possible to have the server return a smaller buffer than what it was expected. And in that case, we would just leak memory from the stack. That's a really interesting feature that unfortunately we don't need fixed. Another one, this one in the query descriptor SMB. So as you can see on this picture, at the end of the function, we are setting different values like data count, parameter count, etc. But look at this parameter count set to max parameter count. This doesn't make any sense. We are just returning a buffer to the client with a large, and saying that, yeah, we are going to return a large amount of parameters. But this max parameter value, it can be arbitrary. So in the end, we are just going to return an arbitrary amount of data, of uninitialized data to the client. Again, a heap visualizer. We don't need that fixed. One of the last one. Again, something like this in restart NT-IOCTL, where you could have, again, like parameter count sent to max parameter count. Yeah, it's gone. And one of my last one, probably the last one, this function in a restart call name pipe, where in case you were using a very old dialect, you could actually trigger an error and have the code return success without initializing the data count, parameter count, etc. So again, you would be leaking everything in memory. Done. Is that all? I wish, yeah, I wish it was all. So I told you that I believe that we fixed around 20 bugs, and we probably fixed some other. Even if we are going to deprecate that protocol, we still support it. Regarding now the exploits, so I've said that none of these from the eternal exploits reproduced successfully on Windows 10. That's true, but you guys are going to tell me, yeah, but there were some exploits made publicly available targeting Windows 10 RS1, for example. And I say, yes, you're right. And it turns out that, yeah, there was one guy who successfully managed to exploit Windows 10 RS1. So this is the anniversary update. And this guy, that was very interesting because instead of corrupting some stuff in memory and redirecting the flow, he just focused on overwriting a token with a null token. And so this would give him the full privilege permissions, the full system permissions on the SMB server. So he was able to write some file anywhere on the drive. That was quite a good exploit. I quite like this one. But still, it took these guys 2 months to write a correct exploit. I mean, something exploiting RS1, which means that our mitigation work, well, it's working. If there is a public exploit that works and it takes you 2 months to adapt it to one of the most recent builds of Windows 10, then it means that yeah, we are winning. We need to defend more, but it's on a good way. And is that all? Well, I believe it's all for me for this talk. So thank you guys for listening. I hope that you have understood some things about this presentation. You guys, we are always hiring at Microsoft and specifically at the MSRC. So the job is really cool. Trust me, you see so many things. So if you think that you've got some skills about that, yeah, trust me, don't be shy. Just talk to me, and I can probably put in touch with somebody who's hiring. Yeah, so the MSRC, so we are split into both the UK and the US. So I'm in the UK, but most of the team is in the US. But still, we are interested by the Chinese hackers. So guys, yeah, don't be shy. Send your CV, and this is a fun adventure. So thank you.
各位有没有什么问题？Any question? OK， 那我们很感谢 Nicolas 给我们带来这个 SMB 的技术细节。那从中间其实我们也发现，就是 SMB 的一些历史渊源，还有 Windows 10， 好 Windows 从Windows 10之后的，我们改进了很多一些核心的安全架构。那我们再度掌声谢谢 Nicolas。
Thanks, guys.